So I'd like to then start this off by pointing out that, hey, some people think of new ideas based upon the current plan. In other words, taking paradise, for example, and then, oh, does that? Well, therefore, I can apply it to this data. That's, of course, deductive thinking. Other people like to consolidate ideas, putting the whole thing together inductively to decide some new creative way of using the current technology. And there's plenty of reason that that's just as valuable as the deductive process. So I'm going to share a little secret with you. And I've always had a love of astronomy, and I took a course back in college many years ago, back when stars were really old. And I think there's a lot of similarity between what we do in the geosciences and what's going on in astronomy of all things. The real fun of astronomy is not so much the process of looking, although you have to gather the data, but it's a process of astronomy predictions. It always rests on observations, and that's true of geology as well. So they are surprisingly similar, and you can learn a lot from learned and revered astronomers. But if you don't write a paper, nothing happens. Or if you write a paper and like some unnamed geologist we know, they just run the other way or go into a catatonic trance whenever they see any mathematics. Astronomy papers would be devoid of any mathematical formulas and would be basically pictures and line graphs and things like that. And that's fine. But what would it be that would interest astronomers? Well, star clusters, different groups. And you'll see in this line of presentation, hopefully, how similar astronomy and geology are related to each other. One of the important aspects of astronomy is the astronomical spectrum, a spectrograph of each star. Now, the advantage of putting a little math in there, believingly or not, is that you can conjure up all sorts of weird stuff like wormholes and time flowing backwards to the singularity of the black hole and things like that. So both ends of the spectrum of astronomy need this. You need to have the pure observation people, and you need to have the wild-eyed, wild-haired, pure theoreticians. They go together. And in the astronomy group, I suspect that incivility would be a surprise. They get along just like we do. So if we look at rocks, the topic of rocks is where we're headed. That's what the series is all about. But we're going to start with the Big Bang, where rocks got started long before crystallization, long before deposition, and certainly long before erosion. I want to share another secret, if you'll allow me, and that is geology is becoming quantitative. It's not if, it's a progress of a process that's already got started, not by choice necessarily, but by necessity. Why is that? Well, quantitative geology is probably not what you think. It's something a little bit different. It's not based upon geology, differential equations. And I'm talking about geology here, not geophysics. I'm talking about geology. But it's neither algebra, nor is it partial differential equations. What is it? It's statistics and probability. It's based upon those sort of things. The sort of things that much easier to get your arms around, the statistical concepts and probability. So these are the two subjects that is becoming embedded in what is contemporary geology and more quantitative, but it's working its way in there. Well, so these two subjects, statistics and probability, are, guess what? Even the mathematics of these two is based on something even more fundamental, because there's a revolution going on. The revolution started in about 1900, 1904, I believe, is literally the starting date. But there's something even more fundamental. It's more fundamental than the statistics and probability. And it's something that encompasses literally all of mathematics. And that is the whole concepts of sets and set notation. Well, now you might think, oh my gosh, Tom, he's gone loony here. I need to either get a cup of coffee or pretend that I'm paying attention, and I'll take a little nap with my blankie and my favorite pillow. But I want to urge you to hang on just a little bit more. Yes, statistics, probability are there. And yes, there is something even more important than that sits on top of that. And that is this business about sets and what is called set notation. I'll go to that, but we're not going to dip into that real deep. But I would like to help you understand what is the value of this brand new thing that's even more fundamental than algebra. And amazingly enough, it has a lot to do with geologic investigations. As an example, a bucket of sand. A bucket of sand is an example of a mathematical set. The bucket itself, mathematically, would be called a set. It's a set of one items. In other words, it's one object. But within that object, we have subsets of several objects. The subsets, each subset has some specific properties, but it also has some common properties. So, for example, let's say that bucket of sand, some of them are quartz, some of them feldspars. Who knows? There may be some other odds and ends, maybe with some calcite pebbles and things like that. Who knows what's in there? Each one of which is going to have a statistical distribution with some common properties. So these histograms or statistical distributions of just doing counting, count your grains, and convert that histogram to a probability for each one of those. Take all the sand, for example, all the sand grains, and make a histogram of the sand grains. Well, we can make a histogram of the sand grains, the other ones in each one of those, and those become a set themselves of a mathematical floor on which we can make predictions to decide, for example, that at this place where we gathered this bucket of sand, there's some evidence of some sedimentary deposition or erosion somewhere up a fluvial river upstream somewhere that's probably off a cut bank somewhere. That's the sort of predictions that we could make, and they're just stronger than just guessing. Stronger, why? Because you've got some numbers. Numbers are always going to help, not replace our insights, but support our insights. These are the 7 parts of this series. We're going to start off with the statistical universe. Why? Why is it statistical? Sets and set notations is our second presentation. Probability, statistics. Once we have the concepts of sets and set notation in mind in that way of thinking, then probability and statistics is rewritten in terms of using sets and set notations. I haven't seen that anywhere. So that material, I believe, will be new for you, but it gives you some valuable insight. There's a lot of math that we've had to endure all the way from, probably junior high all the way through college, where it's making proofs. I hypothesize this, and therefore I start off with these set of axioms, and using axiom 4 and axiom 7, I have one conclusion, and then that conclusion, and another conclusion. I do another thing, proofs. Well, guess what? The whole concept of set notation, the way we use it, in probability and statistics, is more of a description rather than having a set of proofs. And the whole concept there, the valuable insight is, how are is this statistical information displayed, and what are the relationships? We're eventually going to get into Venn diagrams. We're going to get into our Paradise data selector and things like that. The 4th topic is multi-attribute space, natural clusters. From that, we get into looking at things manually and trying to find geologic geobodies and just slap the data up, the wavelet world, and then draw that distinction of the sample world. But it's not just a single number of samples. We're going to be dealing, of course, with vectors. So there may be 4 or 5 attributes. Each attribute corresponds to another orthogonal direction. And we'll investigate. The point is that some of these attributes are not perfectly orthogonal. We'd love to have all our attributes bring us totally brand new information, but that's not the real life. That's not what we work with. We'll investigate that in 5. Then we'll get specific with reservoir characterization. And then we'll deal, the last topic there is the reservoir. The problem is left in 6, and we will move on to reconnaissance work in 7. thinking about what are going to be the tools in the future. We don't have anything in paradise in the 2026 spring to use machine learning, SOM and other technologies. Have no ways of thinking about using it as a reconnaissance tool. What is the business value of a reconnaissance tool? Well, as Deborah aptly points and say, hey, go find me some more of that. I like what I've got here. Punched oil, maybe I've got a reservoir, go find me some more of that. And we see the natural evolution of 3D surveys getting larger and larger. Now, each one of these 7-part presentations take about an hour and a half. I promise that there will be a logical thread of steps that are going to run through these 7 presentations. From the Big Bang into finding more of the same, there's a logical connection. And where we drift away from, that's where we lose people. Lordy, I don't want to lose you. So I promise the following. I promise that each of these presentations, all 7 of them, there will be at least one geological nugget of some geological value in each one of these. So with that, I'm going to switch now to get out of that, and we'll bring this one up. The statistical universe. Before we get started, any questions or comments you might have? Okay, let's go for it. Welcome to our adventure. We know that the universe started with the Big Bang. And we're going to start off with the steps of creation. What are the steps of the Big Bang? Guess what? It's unlikely that everything happened at once. So what are the steps in the Big Bang? What came first? What was the absolute very first thing? I ask you, could you guess? What do you suppose the very first thing was that happened in the Big Bang at the very beginning? What was in the beginning of the Big Bang? Was it a thought or was it something else? So I'm going to ask you to think about this. By pure logic alone, we conclude that the universe started not with some high-speed fluid and soup at a million zillion degrees temperature. It started with structure. Structure comes before substance. Structure sets the stage of our reality. It was the first part of our beginning. So let's take a look at structure of space-time. Yeah, it's space-time. Space and time are together. And we'll investigate this a little bit. The structure of space-time certainly is very basic, and it's often overlooked, unfortunately. There's 2 parts of the structure. There may be more, but here's a couple of obvious ones. First one is called the principle of distance ordering. It says that the closer object obscures more distant objects. We live in that all day, every day, right? You're sitting in traffic and you've got one car in front of you, and then you've got 2 cars in front of you, and the one that's right in front of you obscures the further one, right? That seems perfectly obvious. We leave about it. Hey, we don't even think about the principle of distance ordering. But indeed, that's part of the definition of our space-time. So a distant object is obscured by a near object, and the second structure of space-time is called the principle of time occupancy. What is that? Well, it says that if you have an object in space-time, it requires time to move that object anywhere else, to move it around. So at one instant of time, we've got an object, and we move it outside, or we just move it a fraction of an inch. Everything stands still at a particular instant of time. That seems perfectly obvious. And the motion requires time, but force does not. And the reason for that is actually, I'm on this point right here, it's pretty interesting. That is that motion just doesn't happen. The universe is going to, the macro universe is going to stand still for us, and it's going to require some force to move something around. Newton had that original concept, is that gravity was the force that caused the planets to move around the sun. That was one of the early ones. So at every instant of time, the object does not change shape or size. So structure must have been set before the whole concept of space-time, before it got filled. And it is indeed a part of space-time. Let me give you an example. Here we've got a blob. And we've got two positions here, say a position in the X coordinate and the Y coordinate right there. We've got a near blob. And here's our observer down here. And we observe the near blob and the far blob is obscured. So observation of ordering requires a ray that goes from the observer through a ray that goes out to infinity, and there's only one that is shown. Now you might think, oh my gosh, Tom's really gone over the top of that. But if you just look at space-time and don't include this principle, you've got a really peculiar universe to deal with. If you don't have this distance ordering business, if you could see through everything transparently and you could see simultaneously everything from here to the end of the universe, it would be a very strange and different universe that we would grow up in. And time occupancy, here's our initial blob. And now at this position, here's our initial blob. And as time marches on, we want to move this thing through motion to its final location. Final position goes from here to there, that sort of thing. But we can't do it vertically. We have to have time. So time is required to move it from at this time to that time, just the way it was at this position to that position. So observation of movement requires a ray which extends from the initial blob to the finest. So think about this. Suppose you had a stick and you're going to go ahead and you're going to grab that stick and you're going to move it somewhere. I say we move it over there. All right, we've just done that. What's happened? You had to grab the stick. So you had to first see the stick. Now, I know this seems a little goofy. We're all living in a perfectly obvious reality. And I'm asking you to think about this in a larger concept for just a little bit of time here. You have to see the stick, and you can't see that stick without distance ordering. Then what happens? Well, the principle of time occupancy establishes the order of the big one, cause and effect. Cause, as we know, happens before effect. So after we grab the stick and we want to move it somewhere, we also need the principle of time occupancy. To move the stick, you have to grab it, and the time is required to move the stick to a new position. So we need not only the principle of distance ordering about the grabbing the stick that was the closest one, they also need to have time to move it from one place in the order. And that principle alone explains the source of all cause and effect. Cause always happens before effect. That's just the fact. So space-time is united in a single structure. There's three space directions and one time direction. And that's been tied together probably for well over 120, 130 years, maybe 150 years now. They're all tied together. So time is bound to space. And why do we need to have time bound to space? Can't we get along tinking on rocks and not worrying about space-time put together? Well, hold on a little bit here. Time is bound to space to help us understand the motion of very small particles. The space of the universe changes at every instant of time. If we think about this literally, the camera is like a giant movie, the whole universe in space-time. At every instant of time is like taking another picture at that instant of time. Every point in space is also bound to a single value of time. So do you see why space and time have to be tied together? It's tied together because of the requirements of the principle of distance ordering and that principle of time. So space directions are vectors, point in opposite directions, but time, that fourth one that's tied to the three space directions, that really goes in one direction. It's an arbitrary origin, which we commonly would say, start that at the Big Bang, that's when the clock starts to run, and it extends outward to the end of space, but it also extends forward into positive time going on. So time is a ray that starts and extends into an uncertain future. Observations of receding stars, galaxies, guess what? Astronomically, it suggests that the curvature of space, if there is curvature, is small. So the three space coordinates basically extended perpendicular as a single ray without curvature, without edges. continuing literally to the edge of the universe. So altogether, I hope you understand and agree with me that we live in a united space-time structure. They're all tied together. Let's take a look at this rather weird-looking fella, David Hilbert. The mathematics of space-time is what we call, to give it a fancy name, it's our everyday reality is a Hilbert space. And a Hilbert space is a generalization to any number of dimensions, F, for example, that are based upon the older concepts going back to Euclid of 2 and 3 dimensions. So you have a piece of paper and that's making a map, 3-dimensional space, goes all the way back to Euclid as well. And that's literally going from one point in 3-dimensional space to another. Those concepts of Euclidean space, there is no curvature there, but the Hilbert space also generalizes that and supports that. And those, whereas for this presentation, we're going to take a look at Hilbert space in terms of our space-time, but also a Hilbert space also applies for our SOM calculations, which we'll take a look at later. So what is a Hilbert space? I know you're asking. Well, a Hilbert space is the following. A Hilbert space is F dimensions, and it also throws a couple other things in there to have a qualified Hilbert space. And that is the notion of distance and angles. And that's all put together in one succinct point. And that was, we have one vector in a Hilbert space, P, and we got another in Q. We can form a dot product of those two. In other words, we multiply one times the other, and it's equivalent to the length of P and the length of Q times the angle between them. So with this one stipulation right here, the dot product, the inner product, that adds the whole concept of distance and length and the distance of angles. That gets added to the whole concept of a Hilbert space. So our space-time dimensionality, it's H4. It's X, Y, and Z, and then time T. So you see that what we're dealing with is only one Hilbert space. There's a lot of other Hilbert spaces, but the one that we deal with is a specific one. It's 4-dimensional, and I bet you didn't realize this. And now the Hilbert spaces, Hilbert set things up for his Hilbert spaces, could be real numbers or they could be complex numbers. In other words, they could have real part and imaginary part. Locally, our place in a Hilbert space is a tangent plane, which we approximate with the Euclidean tangent plane, if you will. It's just like saying we can stand having our feet on the solid earth and we can see the edge, and that's where our sunset goes, and it's curved. But locally where our feet are, well, we can treat that as an XY flat plane, that sort of thing. Well, the nice thing about David Hilbert is that we do get a beer in one of David Hilbert's spaces. So we offer a thank you, David. Interesting, brilliant mathematician around the early 20th century.